Okay, let's start. Do you have any questions?
Professor, I had a question. You said
Yep.
that expectation is a linear. What happens if it's not? Is there a case that it's not?
No, 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 no. Absolutely not. Expectations is always linear, and it's a very important property. Um, Variance will not retain linearity unless it's independent, unless the random variables involved are independent, right? But yeah, let me show you. I'm going to say about I'm going to discuss more about that today anyway. But yeah, let's start with that.
Great, thank you.
Mhm. So there are two rules about expectations and variances as follow. The first thing is that expectations are always linear. What I mean by this is the following. The most general thing you can do is you have a sum, okay, of random variables multiplying with the constants and take expectation of that sum. Then the sum, right, will be the sum of the linear combination of expectations. Like that. Okay. And um, what do I want to say here? This is regardless of how the xi are related. So basically, what we're really after here is the joint distribution of the xi, which unfortunately is a topic that comes later, okay, in chapter 5 or chapter 6 of this book. But anyway, so I used a word that has not been discussed, whatever. Probably, right? It's just a word regardless. And well, again, if you want to kind of draw it a little bit closer to home, basically, whether or not the xi's are independent or not, this is always true. Again, independence of random variables are not something we discussed yet, but intuitively, I guess you kind of know what this is all about. Now, again, this is a little bit harder to explain in more details right now. Also, because we haven't talked about joint distribution. But this rule I will kind of use to explain certain things in the lecture today anyway. So it's good that we will bring this up. What else do I want to say here? One of the reasons why this is always true is because at the core of it, main reason, okay, to get more into this requires something else. But the main reason is actually linearity of expectation is really just linearity of integral. Okay, that's all I want to tell you. Because beyond that, we need to look into measure theory, and it sort of involves the law of the unconscious statistician. It might. So basically, I'll just say that it's linearity of integrals. If you look more into this, or if you have a chance to take more advanced courses, you'll see. Okay, but it's always true. On the other hand, right, variances don't behave like that. Variances are not linear in general. The first rule you should know is that variance of a constant times the random variable is that constant squared times the variance of the random variable. Okay? So again, right, notice that linearity would require you to factor it out as the constant itself. That's not true. And this is the most common mistake for students who are new to probability. They will factor a constant out as the constant. No, it's factor out as a squared. Okay. Now, what you might be thinking about is the standard deviation operation, right? Which is the square root, right? Standard deviation of a random variable is the square root of the variance. It's true that, well, but the standard deviation would factor out as an absolute value, right? So again, right, it's not really linear because linear would require you to, factor out as a constant, right? What's the proof of this? Well, the proof of this, right, actually, we'll do the general statement like this, which is something I meant to say today. Variance of ax plus b is a square variance of x. So there you go, right? So a, b here are constants. X is a random variable. So it says that variance, when you add a constant to a random variable, it doesn't change variances, okay? So why? So basically, right, there are two things here. First is that a constant times a random variable factorized as a squared, right here. But the second thing is that variance of x plus a constant is variance of x. So together, right, the two rules come in like this. The reason is because, right, variance of x. Intuitively, right, when you add a constant to a random variable, what do? So you might be used to, right, something called a histogram, right, of a random variable. A histogram, right, is just a chart that shows the likelihood, right, of the random variable taking values at certain places, okay? So these are the values, right? So it's like the support and then the probability of the support, kind of. So if the random variable has this kind of histogram, and if you add c to it, then what happens to histogram? The histogram just moves c units, right, to right or left, depending on whether c is positive or negative. In other words, right, when you add c to a random variable, you do not change the likelihood, essentially. You just change the support, right? You just shift the support. But what is variance? Variance is the spread, right? Measure of the spread. So when you add a constant to a random variable, you change the location, you move the average, but you do not change the spread, right? The spread stays the same, okay? Anyway, right, again, might be a surprise to someone new to probability, but right. So what's the proof of this? The proof of this is pretty basic, right? You just apply the definition. Variance of ax plus b, right, is equal to, well, let me pause, right, and take a step back. So using the linearity of expectation, right? So first of all, variance is defined, right, as the average, the expectation of the mean square error, right, of a random variable away from its expectation, away from its average, right? But if you expand this, right, remember ex is a constant, right, expectation of x. If you want, right, is this. Then it will be expectation of x squared minus 2ex times x plus expectation square of x, right? And now you use the linearity, right, to move the expectation inside. Again, keeping in mind that this guy is a constant. Again, right, remember the notation that e square of x means taking expectation and then square that number, right? But all in all, what we get is expectation of x squared minus expectation square of x, which, right, as I mentioned, is usually 90% of the time the go-to, right, computational formula for variance. This is more like a conceptual formula, right? A definition. They're both the same, right? As you can see, right? The calculations show they're both the same. But most of the time calculating this, in my experience, is a little bit more cumbersome. Calculating this is easier, right? It's the second moment minus the square of the first moment. Anyway, right? So that's variance for you. So to prove this formula, right? You just apply the variance definition. Sorry. Like that, right? And then you expand. Notice that this one, right, is expectation and then squared. So therefore you distribute the expectation inside first. Like that, right? And here, using linearity, you just distribute the expectation inside. Okay, where we also used expectation of a constant is a constant, right? And then we expand this. Okay. And notice, right, what cancel? This cancel, right? This cancel, leaving you with 1 second, right? I expanded wrong, right? This is a squared, right? So leaving you with a squared times this, right? Which is, of course, a squared variance of x. Okay. Any question? So another common mistake, right, that a student new to probability would usually do is that they would mix this with square of the expectation. Again, they're not the same. They're very different. In fact, you can be pretty sure that this usually holds. 99.9% holds. The only time that it doesn't hold is when they're equal, and that's when the random variables are constants. This is called the Jensen's inequality, okay? A particular case of Jensen inequality. And sometimes he'll ask you to prove this. The proof is pretty simple right here, right? The variance is equal to this. And the variance of random variable must be non-negative. Why? Because it's expectation of something non-negative. And so if this is non-negative, then this must be equal to this. So don't mistake the order operation here, right? You square the random variable first and then take expectation. Here you take expectation first and then square it. And they're different numbers. One operation almost always is larger than the other. Okay. Jensen's inequality is more general than this, but this is an instance of Jensen inequality. I'm just writing that so you are aware of that name. We're not gonna really go into that in this class. Anyway, right? So that's one instance or one example on why variance is not linear. But if you want in more generally, then the variance. Oh, by the way, right? Variance of a constant is equal to 0, right? A constant has 0 variance. Constant has, of course, right, constant expectation, right? But in general, the variance of a sum of random variables is not equal to the sum of the variance, like this, right? Even with the squared, you will need to add the notion of covariance. This is yet again the reason why, right? Variance is not linear. Okay, but when the random variables are independent, then covariance is equal to 0, and it kind of looks like it's linear, but it's not, again, because of the square. Now, why is variance not linear? Well, it's that square operation right here. Expectation is an integral, literally an integral, right? We just don't see it that way, but it's an integral. So an integral is linear, but because you take an integral of something squared, it ends up being not linear through that square operation. So that's kind of like the overall details of, these things, right? All you need to remember is this formula, always true. This particular instance, because it's kind of useful, is always there. This formula is always true because it has a covariance. But right now, you're not expected to know this because we haven't introduced covariance operator. But right, the more nuanced details, you can pick it up later on. All right, any question? Okay. Well, let's try to make sure that we understand all this. So I think there is question number 39, right? Which says if expectation of x is 1 and variance of x is 5, then find expectation of 2 plus x squared. What would that be? Any answer? So first obvious thing is to expand, right? And then use linearity of expectation to get this much. For this is 1, right? How do we deal with this?
We can use the definition of variance to isolate for EX squared.
Very good, right? Yeah. So if you know the variance, then you also know the second moment. I mean, you know the variance and the first moment, right? Because this one will be variance of x plus expectation square of x, right? So this guy is 6, right? For these particular ones. All right. So that's the only thing that's worth pointing out. That a lot of times folks don't pay attention, don't notice that if they know the variance in the first moment, they also effectively know the second moment. Any question? All right, so part B, variance of 4 plus 3x. What's the answer?
Three squared times variance of x, which is 45.
45, right? Yeah. Okay. Any question? So again, right, these are the only questions that can be asked right now because we're not at that stage yet, according to the textbook, to talk about interaction of random variables. Notice that these are all about the same random variables. If anything, interacting with its own function, right? But then, using the law of the unconscious statistician, you can view this whole bundle as a single function of x. So it still falls under the, coverage of this chapter. But like I said, right, might as well just start looking at this rule because summing random variables is very natural, as you will see. All right, so let's continue with our discussion, which is about, right, the basic, right, random variables to know, right? Basic discrete random variables. Basic here in quote, meaning that they're not really basic, meaning that if you work out their math, they might as well be quite complex. Basic here is in the sense that they are the ones that people know about, people keep referring to casually, right? If you're in the probability business, statistics business, and you say you don't know the Poisson random variable, that's pretty strange, okay? Things like that. So it's basic in that sense. But then it's nothing basic with these random variables, meaning that you definitely have to spend time, right, to memorize them and to understand them. And so speaking about memorization, right, I did say that sort of the theme here is you want to memorize, right, their mass function, their first and second expectation and variance. Definitely these two. Variance for most of them except for one or two, because variance could be a little bit trickier to memorize, right? But anyway, it's best if you know all of this because, right, as I said, the derivation may not be that straightforward depending on how you look at it. I mean, there will be probabilistic ways to derive them, which I'll mention to you, but these require a little bit more, they're not that advanced, but anyway, right, memorization is one of the best way to do so. So the two random variables we started discussing last time, right, is the Bernoulli, right? So we will say this, x tilde Bernoulli p, right? The tilde notation here is a very common notation, means has distribution of, right? So x has distribution Bernoulli, okay? If what? If probability, so the support, right, is 1 and 0, right? And the Bernoulli, again, is a indicator random variable. It by design, you don't see the indicator, right? But you can associate, right, x with an event. And this is a very, very powerful technique, okay? Right. So then X is a Bernoulli with the success probability as a probability E happens. So the usage of Bernoulli is a lot of times through indicator, right, of an event. And for Bernoulli, expectation will be, right, 1 times P plus 0, 1 minus P, which is just P. The variance, right, is expectation of this squared minus the square of expectation. You can see the expectation of the Bernoulli square is the same, right? Nothing will change. So it's just P. So here, this is P squared minus, sorry, P minus P squared, which is P1 minus P, right? So that's the first. Bernoulli probably, right, is the easiest random variable you can talk about. Nothing simpler than that, unless you count constant as a random variable. The second one is the binomial, right? And by the way, right, this right here is called a parameter, right? Basically, the parameter can change and it will give you different random variables in the same family, right? For 81, for example, in statistics, right, or in parametric stat, right, or point estimator, the goal is to use the data, right, the sample, to estimate, right, the parameters. So yeah, right, the parameter actually is an important aspect of the random variable family. The second one is binomial NP, right? So if Bernoulli, right, denotes the success of an event, then the binomial basically just make it into n IID events, right? So it's n trials, independent, right? You can say n Bernoulli trial, right? Each with success P, right? Easiest example, flip a coin n times and count number of heads, right? With probability P for head. So the values, of course, the mass function is 0 to n, right? Because you can have 0 success anywhere between 0 and up to n successes, right? So to have k successes out of n trials, choose k of them to be successes. Each of those will have probabilities of P to K, 1 minus P to n minus K. Each of those scenarios, right, among the n choose K scenarios, each of them has this probability of happening, right? So like that, right? So that's a mass function of a binomial. Well, what else? Expectation, right? Now, if you go by formula, expectation will be sum of k, n choose k, p to k, 1 minus p to n minus k, right? And we spent, I remember, something like, yeah, roughly 5 minutes, right? Maybe a bit less to derive this, to simplify and remanipulate this formula, right? The trick is not that hard. Do a cancellation here, do an adjustment so everything looks like n minus 1, and use the binomial formula, right? Etc. But the answer is just n times p. And this is exactly one of those things where I said, right, it's easier to just memorize rather than, right, kind of prove. Of course, if you are very interested in the math and you like combinatorics, you definitely want to know, right, how to do this, because it's just a very easy combinatorics trick anyway, right? But if we are just doing work using the binomial, then there's no reason that each time we rederive the formula for 5 minutes, right? That's just inefficient, okay? For the same reason, right? For example, the variance of x, which is expectation of x squared, right? Minus expectation square of x. Well, what does it take to calculate the variance? Well, we know expectation already, right? So we need to know the second moment. That's always a theme. Knowing the second moment is necessary, right, to know the variance and vice versa. So notice that to do the expectation, the second moment here, what we'll need is k squared, n choose k, p to k, 1 minus p to n minus k. And this guy is a fun one to go through. Why? Because you cancel k once, and you will have, k minus 1 factorial. So the question is, you have k left here. How do you cancel one more time? Easy, right? You just change this to k minus 1 plus 1, etc. But the trick is going to be 10 minutes worth of calculation. Leading to what? Leading to this result, right? Not the second moment, but the variance will be np1 minus p. And I think that's a much easier thing to memorize than how to handle the calculation. So if you're interested, I'll recommend you to read the textbook or figure out yourself, right? I'll be happy to go through the calculation during office hours or something like that. I don't think it's that educational to go through this, right, in class, okay? So besides, I'll tell you another probabilistic way to derive this, right, which is my preferred way of explaining these things. The reason is, right, I kind of mentioned this at the beginning of the class. We do probability because it's different from combinatorics in some way. If you use combinatorics to solve probabilistic problem, it's valid and it's a great way. But in that sense, then probability should be a subfield, right, of combinatorics. It should not be an independent field, right? It's independent because you can use independent thinking to solve a problem, right? So anyway, right? So to recap, binomial, expectation NP, variance NP1C. Now, what's a probabilistic explanation for this? The probabilistic explanation for this is also the very important connection between binomial and Bernoulli, right? It's kind of already kind of alluded to here. A binomial is n independent Bernoulli trials, right? Which count the total number of successes, right, in n trials. When you hear the word total, you can be pretty sure there's a sum behind it somewhere. So here's the thing. If x is a binomial NP, then you can write x as a sum from 1 to n of xi, where xi are IID Bernoulli P. IID is a very common word in statistics. It means, in probability too, right? Independent and then identically distributed. Okay. So basically just the sum of n independent Bernoullis, all probability P, right? You think about it, it's just common sense. If you want to know the total number of successes in n trials, you just sum, right, over each trial. If it's a success, you sum 1. If it's not a success, you sum 0, which is really counting, right? You go through the trials and you count 1, and then 2, and then 3, etc. You get total number of successes, okay? But this representation will give you more than you think you can have. For example, what is expectation of x? Well, expectation of x is an expectation of this sum by definition, but expectation is always linear, so we can pass it inside. But once we pass it inside, then things are easy because now we're dealing with expectation of Bernoulli, which we know is P. So that's NP. Okay. Variance is variance of the sum. Now, I did warn you that variance is not linear, but it is when things are independent, which we have here. So we can, again, pass the variance inside. Or you can just say that because the covariance is 0, R0 here, what's the variance of Bernoulli? P1 minus P. And that's why it's NP1 minus P. There you go. Notice, right? This takes 2 lines of calculation versus the combinatorics way of calculating, which is at least 10 lines or so. But of course, right, it requires a different way of thinking, which is also sophisticated. So it's not that it's easier or harder, right? Just a different way. Any question? All right, so let's see an application, right? This is question number 43, right? A and B take the same 10 question. Exam. Each independently answer correctly by A with prop 0.7 and by B with prop 0.4. Okay. A. Find the expected number of questions answered correctly by A and B. How will we answer this question?
Is it 10 times 0.4 times 0.7?
And what's the reason?
It's like a binomial sort of distribution where they answer each correctly. Like if they both answer it, it'd be 0.7 times 0.4. And you can think of it as like 10 trials since there's 10 questions.
No, that's excellent. That's exactly what I want you to realize, right? That here you should recognize that what they're referring to is a binomial with 10 trials and success 0.4 times 0.7 times 0.4, because that's exactly the probability that A and B answered the same question, right, correctly. Yes. But once you recognize that framework, then things just take its course. Meaning what? Then you just apply formula. For example, right? We don't have to stop here. We can ask what's the variance of the number of questions answered correctly by A and B? And the answer is 10 times 0.28 times 1 minus 0.28. That's it. All coming from recognizing that. And that's the power of model, right? The moment you get into the right model, emphasis on the word right? Because if you identify the wrong model, then well, it's gonna be wrong, right? But the moment you identify the right model, then things take its course, right? So That's really what model thinking is about. So yes, right, we find the variance of the number of questions and answer correctly by either A or B. Well, the answer is
This is a binomial distribution with a probability of what, minus 0.3 times 0.6. And then you can just use the variance formula.
excellent, right? Excellent. Yeah, correct. Yeah, right. 10 trials. They both get wrong. And so this is either one of them get right? Correct. And yeah, you just use a variance formula. That's correct. Very good. Any question? All right. So let's move on to the next random variable. The next one, let me see here. Is the Poisson. Yeah. Okay. So Poisson has one parameter called lambda. Okay. Now, so X has a Poisson random variable with rate lambda, with average lambda. If, right, the probability mass function will be e to minus lambda, lambda to the k over k factorial, where k runs from 0, 1, 2, etc. So emphasis on this, meaning if this is the first time you see this random variable, is probably the first random variable that has no upper limit, meaning that upper bound, meaning that it can take on any finite values. Okay. Well, pay attention. The Poisson does not take on infinite value. Okay, that it means it always takes on finite value, but the finite value has no upper bound. Okay. So there are many things to talk about. Maybe let's just first prove that this is a bona fide, right, probability mass function, meaning that we should check that the sum from 0 to infinity of this, right, is equal to 1. Now, notice that we did not do a check for the Bernoulli because it's obvious, right? We did not do a check for the binomial because it's just a binomial formula. But what about this? Well, it's worth noting then, right, that if you sum this, the sum is over k, right, over the values the Poisson can take. So e to minus lambda is a constant that factors out. And we recognize this as the Taylor series expansion, or e to lambda, right, from Calc 2. So that's indeed 1. And in fact, right, if you want to operate with a Poisson, exponential series expansion will be very, very helpful. Okay, it just pops up here and there. So let's give some some calculation to note. For example, if x is a Poisson lambda, what's the probability x greater than or equal to 2? Well, maybe you're thinking of summing, right, the probabilities from 2 to infinity, which is correct, where it's not going to be very informative. With Poisson or with infinite distribution, with random variables with an infinite support, try to pay attention to complement, because it would give you, right, a compact answer. So like that. Do you understand? Any question? So let's talk expectation and variance. Expectation of a Poisson and variance of the Poisson are the same, and the lambda. They're the same in terms of value, but might as well tell you about unit, right? Suppose x has some unit, I don't know, meter or whatever. X has unit, let's say of length, meter, feet, whatever. Then expectation of x has what kind of unit? And variance of x has what kind of unit? If x is meter, expectation of x will be in meter. But variance of x will be in unit of length squared. It'll be meter squared. Okay, so you do math, you don't see units a lot, but of course you learn probability to apply it to many fields. So right, that's sort of the reason why when you multiply a random variable with a constant, it pops out as a square, right? Because the unit of the variance actually is a square. All right, so it's a standard deviation that has the same unit as the random variable itself. But variance, right, has unit of whatever the random variable is squared. So in that sense, right, when we say expectation and variance of the random variables are equal, it's sort of like a okay thing to say in math. But if you factor in a unit, then this is kind of like comparing apples and oranges, because one is in the unit of length and one is unit of length square. Okay, but they're both lambda, so that's kind of the point. Maybe having said that, let me separate the two out just to not compare apples and oranges. Okay. Now, as the proof of this statement Well, we have nothing better to do than just to pull out our good old calculation. So expectation of x will be the sum, right? K times e to the minus lambda, lambda to the k over k factorial, right? So again, right, the usual trick of division by k. But let's note something, right? When k equals to 0, again, right, when k equals to 0, the 0th term doesn't contribute to the sum because it's 0 times something. So we might as well bump the sum up to 1, right? And nothing change. Nothing will change, right? Like that. And of course, we want to line everything up with k minus 1, so we factor out a single lambda. But you see, right, if you change index, and we just prove, right, that this sum is 1, so that's lambda, right? Well, what about a second moment? So it'll be the sum, right? K squared e to the minus lambda, lambda to k over k factorial, right? So again, we cancel one single k, and we can bump, right, the sum up to 1. Right? And so now you see that to match up everything here, we factor out a lambda, but we also do a subtract 1, add 1 trick. So it will be k minus 1, right? E to minus lambda, lambda to the k over k minus 1 factorial, and then plus 1, right? Plus 1 back, which is adding this caboodle back. Yes. So that's a subtract 1 plus 1 trick. But we just show, right, that this guy is what? This guy is lambda, right? So this is lambda. Right, so we just have to handle this. To handle this again, right, you factor out a single lambda. And then you see, right, that you can change index back to 0, right? But this is just the expectation of the Poisson. So as the number lambda, your lambda squared plus lambda. Well, variance, right, is expectation of the squared minus the square of expectation, which is lambda squared plus lambda minus lambda squared, which is lambda. Again, you see, routine calculation, not super hard, but yeah, right. Might as well just memorize it. Any question? Okay. So let's talk about the modeling aspects of the Poisson. So the modeling aspect of the Poisson is as follows. Poisson is probably a famous thing that you would have seen in many contexts, right? There's something called a Poisson process, point process, for example. So Poisson as a random variable, you might hear the following. Poisson is used to model rare events. or rather, right, to be more precise, the number of occurrences of certain rare events. But if you want, you should say in the time window. And for this reason, it's also just say arrival of events in a time window. And so we omit the word rare, but you might hear the word rare associated with the Poisson, and I'll explain why. But what's some pretty common examples that would kind of kick in the Poisson kind of context? Number of people arriving at, say, an airport or a store, whatever, in a time window. Let's say in an hour, or a day, a week, whatever. Well, here I don't mean, right, they're all the same. Each of these would be a different Poisson, random variable, okay? In fact, right, the difference between these guys are probably, if it's the same store, the lambda, right? The average number of arrivals. Lambda here, right, in this context, X represents the number of people arriving at a store, then lambda represents exactly the average number of arrival at that store in a unit of time. Earthquake is also a very popular thing to be modeled by Poisson, and hence the word rare, right? Number of earthquakes at a certain location like California, right, in a month, let's say. Let's say in a year, in a month, right? Something you might not expect, such as the number of typos on a page of a book. Can be described as a Poisson. Now, so something is pretty funny like this, right? Number of people arriving at a store. Technically speaking, that you can imagine a cap, right? There's an upper limit. Maybe you can say there's no limit, but well, I doubt it, right? I can be pretty sure 10,000 people cannot arrive at Macy's during a day, or if you want, 1 million. Because, right, theoretically, the Poisson, right, has no upper limit in the number, in the values can take. But you can see, right, yeah, as k gets large, right, the k factorial grows really fast. And lambda to a k also, of course, grows exponentially, but it's nowhere near, right, the rate of k factorial. So therefore, even when k equals to 10 or so, right, as long as lambda is not too large, you start to see probability being very minuscule, like close to 0. So in fact, right, the Poisson, if you graph the histogram of it, right, it probably decays very quickly. So the first 10 values or so, right, sometimes even the first 5 values, mostly capture 99% of the mass of the Poisson. And that's why, right, things that somehow seem like have a cap, right, the number of typos on a page of a book clearly cannot go beyond the number of letters, right, on that page, whatever. But in some spirit, it's an approximation. In another spirit, it's a model. But right, the Poisson, even though yes, right, in theory, it goes on to infinity, but in practice, if you look at the mass, 99% of it, like I said, gets concentrated around the first 10 values or so. So yeah, these will be the typical things. And notice, right, Poisson, of course, is integer value, right? It's integer value. So if you have something that's non-integer value, like a fractional, well, you can maybe try to modify into a Poisson, but by itself, it cannot be a Poisson, right? A Poisson has to be integer value, right? You cannot have a fraction of people arriving at a store, whatever. So a historical, funny, amusing rather model, right? Using the Poisson is, I think the number of officers die by being kicked by a horse in Britain back in the day. I don't know, right? Being kicked in the horse by a horse is like a rare event or something, but it was used as a Poisson model. So, but just an amusing model. All right. So what else? One thing so two things. Poisson has many properties. I just cannot tell you all of them. They will kind of stretch beyond the current level, right, of discussion, and also beyond this course. But something to note as follows. Poisson has a very interesting property that if you sum independent Poissons, you get Poisson back. This will revisit later on when we discuss moment-Jane function. But I might as well tell you now, right? So you kind of at least be aware of that. What this means is following. If X is a Poisson lambda 1, and Y is Poisson lambda 2, then X plus Y will be Poisson lambda 1 plus lambda 2. Well, it is, in some sense, it's not that surprising in this way. If you look at number of people arriving at two different stores, right? One with rate lambda 1, one with rate lambda 2, and you add them up, well, it sort of makes sense that the total number of people arriving at these two stores is Poisson. But more commonly, you can add the number of people arriving in consecutive hours, right? Each of them is a Poisson random variable to get the total number of people arriving, let's say in a day. When you add up, like, let's say the 12 hours, right, that the store opens, each hour being an independent Poisson, right? So then that's how the connection between the number of people arriving in a day with the number of people arriving in an hour, right? You sum up the number of people arriving in each hour, each of them being independent Poisson, you get the number of people arriving in a day, which also preserves the Poisson distribution, okay? So we'll revisit this, but this one, the one I'm telling you next, I think will show up even in this chapter. It's called the Poisson approximation for the binomial. And again, this is kind of the one that explains why it's a rare event. It says the following. If you have a binomial NP and you let n goes to infinity, p goes to 0 in such a way that n times p stays constant, then X will have approximately a Poisson lambda distribution as n goes to infinity. And it's exactly here, the p goes to 0, that sort of earns a Poisson the name of a rare event. So what's happening here? What's happening here is that, you know, you kind of have a lot of trials. Don't get too bothered with the n goes to infinity. In practice, maybe 30, but the p must be pretty small, like 0.01, okay? Then what you're having in your hands is like a lot of trials, but each of them has a very small chance of success, okay? In that scenario, right? And that's why it's called a rare event. Then if you look at the number of successes, okay, you have across this so many trials, you can approximate it pretty well with a Poisson, with rate equals to the average number of success you have across all trials. For example, right, you see that's where the typos on a page work. Hopefully, right, each letter has a very small chance of being a typo, right? A letter being a typo is a rare event. But then across a page that has a lot of letters, then, right, so typically, so here's the issue, right? Suppose you have p equals to 0.01. Let's say n equals to 50. If you want to calculate, let's say, probability that you have, I don't know. So x is binomial NP, right? With this much. If you want to calculate, let's say, probability x equals to, let's say, 20, then what do you have? You have 50 choose 20, 0.01 raised to 20, and 0.99, right, raised to 30. Okay. Now, one thing that I think you guys, and to some extent my generation, gets spoiled about, right, is that we don't appreciate the nuance of this kind of calculation. I mean, you can still do. For example, if you try 50 choose 20, okay, you try to use any calculator to do 50 choose 20. I'm pretty sure your calculator will blow up unless you use a software that can handle like large numbers, because 50 choose 20 is a pretty big number, right? So back in the day, when say calculator can handle only 9 digits at most, or even back in the 18th century, there's no realistic hope of calculating out this number, right? And then the error accumulating, right, when you do 0.01 raised to 20 is huge. So all in all, right, this number will come out as a very big error. But if you approximate it as e to minus what? So here lambda is what? Lambda is 0.5, right? So e to the minus 0.5, 0.5 raised to 20 over 20 factorial. Well, maybe I am a little bit guilty of false advertisement because 20 factorial is not a small number. But all in all, right, you can see that it's still a more tolerable calculation, right, compared to 50 choose 20 and this kind of things. And this is why, like, the Poisson approximation for the binomial can be a useful thing to keep around, right, for dealing with p small. But right, that's the emphasis. But for p approximately 0. For p large, this approximation will be nonsense. It's not good at all. There's another one called the normal approximation to the binomial, which is more famous, right? This one is only when p goes to 0. Any question? All right, so maybe let's try something to demonstrate this. So quiz 3, right? Suppose that earthquake happens in the US. With lambda equals to 2. So let's say with rate, right? 2 earthquakes with average rate, right? Of 2 per week. Okay. So on average, there are 2 earthquakes in the US per week. Okay. find the probability that 3 earthquakes occur during the next 2 weeks.
Professor, is this exactly 3 or 3 or more?
Exactly 3. Exactly 3. That's what the textbook was saying. Exactly 3. The answer is so you would use Poisson, right, to answer this question. The question then is a Poisson with what kind of rate? The answer is a Poisson 4, or rather a Poisson 2 times 2 or 2 plus 2, right? Well, I guess the 2's kind of gets a little bit confusing, but the first 2 is a 2 from 2 per week, but then you get 2 weeks, right? So that sort of comes from what I explained, right? When you have independent Poisson, earthquakes, right, on different weeks should be independent. And if you sum, right, the earthquakes on each week, you should get the earthquakes in 2 weeks, right? And so those add together to get 4. Does that make sense? That's the only thing that sort of would be difficult about this, right? Like that. Any question? All right. So let me give you examples, right? For, let's say, question number 54, 55, 56, all right? And even 57. And I think I'll just briefly write down what they say. Number 54 says, expected a typo on a page of a magazine is 0.2. Find a probability that next page contains 0 for A, and then next page contains 2 or more, right? Typos. Number 55 talks about monthly worldwide airplane crashes is 3.5. Find the probability that at least 2 accidents next month. Probability at most 1 accident next month. Number 56 says approximately 80,000 marriages took place in New York last year. Find the probability that at least one couple both partners born on April 30th. And then the probability both partners celebrate the same birthday. I mean, yeah. Okay. So whatever, right? The specifics of each question can be a bit different, but I want you to recognize that they all are what? Poisson types of question. You see? So they just kind of maybe gets a bit more nuanced in terms of the language and stuff like that, but they're all Poisson type of question. For example, right? 54 straightforwardly talk about what? A Poisson 0.2, right? And it looks at probability of x equals to 0 and probability x bigger than or equal to 2, which, right, as I explained, should be done via 1 minus, right, probability x equal to 0, right? Like that. 55 actually is just a repeat, right, of that. But instead of Poisson 0.2, they talk about Poisson 3.5, right? So, and then actually it's even the same kind of, right, language. So let's look at 56. How would we phrase 56 and what, yeah, what kind of, or why would we expect it to be Poisson, for example, things like that. So note, right? Yeah, go ahead.
We could have a Poisson of when the couples have the same birthday. So for example, like 365 squared. So have the 80,000 divided by that.
Divide, multiply by that. So, right, this is exactly the case of a very large number of trials. 80,000 is number of trials. And whatever event they're referring to, right? Both born on 4/30th. is exactly the P. Doesn't make sense? So that's exactly what I was explaining here, right? The number of trials is very large. The success probability is very small. Then the average, right, is lambda. Oh, by the way, right, I think I forgot to tell you this. Here's a consistency between these two, right? NP is what? NP is expectation, right, of a binomial. And you see, expectation of a Poisson lambda is lambda. So that's why NP equals to lambda. But more than that, right? What's the variance of a binomial? Variance of a binomial is NP1 minus P, right? What's the variance of a Poisson? Variance of Poisson lambda is lambda. Now, if NP is lambda, how do we justify that NP1 minus P is also lambda?
1 minus P is very lot or very close to 1.
Correct, right? Exactly. So it's actually because P is close to 0. So everything's consistent from that point of view. So you can see why. That it sort of like maybe gives you a clue in memorizing why variance of Poisson lambda is lambda as well. But anyway, right? So here, for example, the success for part A will be defined, right? Clearly is what? Both born on a single day, right? Maybe 4th of July, you know, to make it into a movie, right? Both born on 4th of July, whatever. So, of course, then P here is, right? I mean, if we take a day as one, a year having 365 days, then that's the success, right? But then lambda will be 80K times that. Does it make sense? N times P. And then this is just a Poisson lambda. So you're asking for probability of X equal to 1, which of course, right, is 1 minus power X equals 0, which is 1 minus E minus lambda for question A. Do we understand? What about question B? Is it the same kind of Poisson?
No, because our P can be just 1 over 365.
Yeah, right. It's just a change of P, but 1 over 365 is still pretty small, right? Because it's 365 times 1 over 365 squared, right? Which is 1 over 365. But then, right, lambda will be changed, right? Still, right? Whatever. Are we okay? Oh, wait, hold on. The language is a bit weird. Let me check. It didn't say how many, right? Oh, sorry. At least one couple where it's still that kind of language. Sorry. At least one couple where both celebrate the same birthday, right? So still that. All right, any question? Okay. So with that, we finished 4.7. So 4.7 was Poisson. So now 4.8 is about geometric and negative binomial and hypergeometric. So let's talk about geometric. All right. So with Poisson, I kind of stated, right, the mass first, the distribution of the mass first, and the model later. But most of the times, these are more easily memorized by the model. For example, a geometric P, then it represents the number of trials, right, with success probability P. Okay, let me just say this. The number of trials until the first success. Okay. So basically you have independent trials, IID trials, independent Bernoulli trials with success probability P. Okay. Well, that's kind of a long description. Short description is you flip a coin, right? With probability head is equal to P, and you count the number of flips until the first head. That's your geometric P. Okay. So with that description, right, what's the support? What kind of values can you take? What kind of values can a geometric take? Can I take value 0? No, right? Because you need at least one trial for a success. So unlike the Poisson, right, and binomial, geometric starts at 1. And then what? Increases, right, by 1, because who knows, right? You can have 2, 3 trials, etc., before you have a first success. Well, just to be clear, right, we know what we're looking at. It's something of the type tail, 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 and then head, right? Something like that, right? Where tail represents a failure and head represents a success. So here, for example, right, this is a 6 for a geometric, okay? But from that point of view, right, is there any upper limit to the value of a geometric? Answer: no, right? I mean, it's a bit counterintuitive, but at least in theory, you can keep on tossing for a long, 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 long time before you see a first head. Of course, right, the probability of that happening is really small, like 1,000 tails and 1 head. Probably you won't see it in your lifetime. Who knows? But in theory, it has a non-zero probability, so it's still there, right? Now, what's the probability that happens? Meaning that it takes you k trials until you see the first success. Well, it's pretty easy, actually. These are the only ways, right, the trials can happen, because you have to have the last one as a success. Everything before it must be a failure. So it will be 1 minus p raised to k minus 1 times p. Okay. So let's check if we sum all these values up, do we get 1? or you can see, right, that this is a geometric series. So using a geometric formula where we use the first term, right, which is 1, because when you plug in k equals to 1, you get 1, divided by 1 minus the ratio, you do indeed get 1, right? So, and also, by the way, that's why I call it geometric, right, random variable, because the distribution is exactly a geometric series. All right, so what's the expectation? Well, as you can see, right, the expectation formula will ask you to compute k, 1 minus p to k minus 1 times p. Well, this p doesn't matter, right? It can come out. But how do we calculate this thing? Well, it turns out there's a neat trick. By seeing that this is the derivative with respect to, let's say, p of 1 minus p to a k. Rather, it's a minus, right? Because differentiating 1 minus p gives you a negative sign, right? As a chain rule. Do we see that? Differentiate to p, right? You get k times k minus 1 minus p to the raised to k minus 1 with a negative sign. That's why. Yeah. All right. So, well, why would this be helpful? Oh, by the way, right, this is a negative sign. It's not p minus that. So let me just make sure we understand that. So this is helpful because now this is, again, a geometric series, right? Indeed, it's going to be, what? Hold on. Yeah, it will be, right? P times, right? The first term is 1 minus p divided by the ratio, which is p, right? And this derivative with a minus sign, right? Well, let's see. Probably we don't need to use the product rule, right? So you know what? Let me put a minus p, right? Instead of doing that, minus. So you got 1 over p minus 1 prime, right? Which is really just 1 over p prime, which is minus 1 over p squared, right? And you see the glorious final answer is 1 over p. There you go. Expectation of x is 1 over p. Again, demonstrating what? The calculation can be pretty, a little bit tedious to get to you something that, it's sort of intuitive anyway, right? Now, so if you have a trial with success, let's say 1/10, you kind of expect 10 trials before you see a first success. That's what I say there, right? But so again, when we see a geometric, we just memorize that. We don't have to really rework the formula. And you can see, right, the calculation just gonna get a little bit more nasty when it comes to k squared. Because, right, we can't really say that this is the derivative, right? Because if you bring down 1 minus p to k, you only get k down. The next one, you get k minus 1. So not only that we have to look at the second derivative, we also have to deal with the k minus 1, etc., etc. So this is exactly one example where let's just not even bother and memorize the formula. And the formula is variance of x is 1 minus p over p squared. Okay. You can do it. You can work out all the details there with a calculus trick, but I'll just let you see the text. I don't think there's anything super eliminating there, right? So as far as I'm concerned, I think the variance of a geometric is something I don't carry around with in my pocket as much. The expectation is used all the time. So you definitely must memorize this. This one, yeah, you can put in your formula sheet, look it up, whatever, right? I don't see this being asked as often as expectation of a geometric. Doesn't mean you don't need to know this. It's just that if you, let's say, don't memorize it as much because of lack of use, that's understandable, right? But still, you should know where to look it up when you need one. Any question? All right. So let's look at the negative binomial next. So a negative binomial has two parameters. It's n and p, all right? So it looks deceptively like a binomial in terms of the notation, but there's the word negative in front of it, okay? So that makes a huge difference. So negative being neg in p. So what does it model? First of all, it models the number of trials until the first, let's say, nth success. All right. In independent trials. With success probability. Okay. So as you can see, this is just like the binomial. It's sort of like a general quote version of a Bernoulli. A negative binomial is like a general version of a geometric, right? Because a negative binomial, when n equals to 1, is exactly a geometric P. Okay. So first of all, right, what kind of values can a negative binomial take? What kind of values can a negative binomial take? Oh, you know what? I apologize. The textbook doesn't use the word n here. They use r. So I just want to kind of stay with the textbook notation. What kind of values can the negative binomial take? What's the minimum value must it take? Can it take?
R and upwards.
Correct, right? So the minimum values is r because you need at least r trials, right, to see r successes. All right, so what's the probability it takes on a specific value, like k? Well, so what must happen? So you have k spots, right? Where you know that the last one must be a success. Why? Because it's the number of trials until you see the first rth success. Meaning, right, the moment you see the success, the rth success, you stop. The last one is a success. Okay? But then what else? What else is in the previous k minus 1 trials, you must have R minus 1 successes, right? In order to guarantee that there's R successes total. There are R successes total. Do you care where those R minus 1 go? The answer is not really, because wherever they are, right? As long as there are minus 1 of them there, then this last one will make it the first R successes. We understand? Therefore, right, the notation is, or the answer is K minus 1, choose R minus 1. Among the first K minus 1 positions, choose R minus 1 for the R minus 1 successes. And that's it. You need R successes and then K minus R failures among those. Any question? Now, with the negative binomials, right, for example, when you try to verify that it's a distribution and you sum K from R to infinity, right? Do you see, at least I vaguely remember that somehow this has something to do with the negative binomial concept in combinatorics. I just don't remember how it is anymore. But the thing is, right, you see that it's, at least for me, it's not an obvious calculation. Because notice, right, the K here, the running parameters is K, right, which is the upper one. So, right, normally when you do binomial formula, you fix this and you sum up over this one right here, right? But now this is fixed and you're summing over this. So it's sort of like the opposite, right? Whatever. And so that's probably one of the reasons why it earns the name negative binomial. But all in all, right, this is why I say, like, sometimes, right, I mean, the probabilistic argument is quite clear. This must be the distribution. Why? Because this is the model you're looking at. But if you ask me to prove right now that the sum here is 1, I'm not so sure, right? With this one at least. And I probably have to consult a combinatorics textbook, right, on how to handle this, etc., right? Point being, right, is that if you take expectation, for example, then you have to sum K times this. Anyone care to guess what this will be? The answer actually is easier than you think. The answer is actually R over P. And it's not a coincidence. R being what? R being the R of the R successes. And 1 over P being the 1 over P of what? The 1 over P of the geometric. Okay. So what are we saying actually? And let me write down the variance, right? Anyone care to guess what the variance of a negative binomial is? It's going to be R 1 minus P over P squared. Which is what? R times the variance of a geometric. Does this sound familiar? It's exactly, right, the relationship between a binomial and a Bernoulli. A Bernoulli has expectation P, a binomial has expectation N times P, A Bernoulli has variance P1 minus P. A binomial has variance NP1 minus P, right? So what's the reason there? The reason there was because a binomial is a sum, right, of independent Bernoullis. Do we have the same thing here? You bet, right? If you have X to be a negative binomial, then X can be represented as a sum of R geometric random variables. Okay? Why so? You think about it. You count the number of trials until the first R successes, right? What must happen? Well, you must have the number of trials until the first success. Then from there, you need to have the number of trials until the second success. Well, you think about it. From the first to the second is really just repeating, right? The first success. So the second success is like the first success after the first success. The third one is the first one after the second, so on and so forth. So therefore, right, it's really the sum of geometric. And once you realize it's a sum, then expectation and then variance follows. And because of independence, expectation and variance follows the rule of the sum. Again, right, the passing of the variance inside a sum is because, right, of independence. Otherwise, we don't have it. But there you go, right? That's the easiest way to memorize a negative binomial. It's a sum of independent geometric, and relationship just follow that way. All right, any question? So let us end the class with a, this is quiz 5, right? Problem called the Banach matching problem. Banach is a famous mathematician, right? So a problem named after him must be an interesting problem. So this is probably an old time, but you have a mathematician who smokes, right? Carries, so 2 matchboxes. Okay. One in the left pocket and one in the right. Each time they smoke, they're equally likely to take from each box. So suppose that they found one of the boxes to be empty. So here the 2 matchboxes start with each has n matches, right? Okay. So find the probability that the remaining box has k matches left, where k equals 0 up to n. All right, it's probably a little bit long to describe, but you have two boxes, right? Each with n objects. Equally likely to be used, right? One at a time. So you can say remove without replacement. And then, right, of course, one box will hit 0 first, right? At that moment, what's the probability that the remaining one, the one that's not empty yet, to have k matches left, k objects left, right, from 0 to n? Well, maybe the easiest, not the easiest, but probably start working with, let's say, edge case to get a feel on what happens, right? What's the probability that remaining box has n matches left?
One half to the
This means,
p
yeah, 1/2 to the
n.
n, right? Correct. Because, right, that means the person must keep picking from the same, right, box n times, right? What about the remaining box has n minus 1 matches left?
One half to the n plus 1 times n plus 1 choose 1.
So 1 second, right? With this one, I'm wondering if there's a 2 multiplying, because it could be either box, right? So let's just, maybe there's a 2 times here, but let's pause on that a little bit. But what are you proposing? What is the answer here?
I said 1/2 to n plus 1 times n plus 1 choose 1.
Like that. Okay, what's the reasoning?
Because we have to choose from each side n plus 1 times, and then we have to choose from the remaining box once, which is the choose one.
Right, but you fail to consider one thing, right? So, sort of roughly speaking, the right argument, but right, when you say n plus 1 choose 1, that means you can pick right from the remaining box one time. But notice, right, there's one important description here that you did not pay attention to, which is the person found the box to be empty, right? That means, can he pick the n minus 1 match left at the last time? He can't, right? Yes, he did pick it n plus 1 times. He did pick them n plus 1 times. However, right, the time that he picked the one from the left, the one from the box that's left, must not be n plus 1, but must be something like n choose 1. Because only in the previous n times, does it make sense, that he can pick that one? Because if he pick it at the last time, then he will not discover, right, the box to be empty. Does that make sense? So
I see,
in
yes.
this way, right, this should remind you of the negative binomial, right? In the sense that you would have something like a success, whatever that means, right? And then the failures being the one that's remaining. So if you can carefully frame this language into, right, what's a success and what's a failure and how many times, right? Because again, the description is that he will found box to be empty. So the ones that he picked from the other one must not occur, right? Must not occur at the last moment. Things like that. All right. So I think we're running out of time here. So let us revisit, right, this problem more carefully next time, okay? And then we can more on this issue. But yeah, to be continued on Wednesday.
Thank you.
Sure.